Thanks, Avi. Thank you for coming. So I was a postdoc here 20 years ago, and it's great to be back here. Let me talk about some of this. Part of this would be to, demystify this Moser Tardos procedure, which is really, very nice breakthrough on the problem, and to talk about further extensions. Following work of Moser in 2009, which itself was a breakthrough, Moser and Tardos basically showed how to make constructive most applications of the local lemma. I'll give you a proof sketch, and hopefully a little more intuitive than the branching processes that they use, and we'll see how to go beyond Moser Tardos. That basically what I'd like to convey is that Moser Tardos actually is not just an algorithmic version of the local lemma, but actually is a probabilistic process of interest in its own right, which needs further understanding actually. So it already helps us go beyond the local lemma, but I think there is more to be understood here. So I'll start with some a brief description of some work I did with Heupler and Shaha a few years ago. So as all of you know, the local lemma is a powerful probabilistic tool, and one of the interesting things in the probabilistic method is that for most applications of the local lemma, actually their only known proof is using the lemma. And let's talk about the breakthrough that Moser and Tardos came up with. So the local lemma is a little more general. It talks abstractly about events and dependencies, but essentially all applications in computer science fit the following framework, where your bad events, the events that you want to avoid, are actually driven by some underlying independent random variables, right? So this is called the variable version of the local lemma. Is a slight specialization of the original lemma, but covers essentially all applications we care about. So imagine some underlying independent random variables x1 through xn, and then you have bad events e1 through em, each of which is a Boolean function of some subset of the ei's, right? So for example, e1 could be some function of x1, x5, and x8, and so on, right? And therefore, since these xi's are independent, you naturally get a dependency graph on the ei's, which is basically the intersection graph of these subsets basically. So e1 and e2 are dependent because they share a variable, which in this case is x5, but e1 and e4 are independent because their sets of variables are disjoint, right? So for example, you can think of this as a 3-sat instance where each ei is the bad event that a particular clause is violated basically, right? And of course, the whole thing of the local lemma is sufficient conditions under which you can avoid all of these simultaneously. In other words, what you want is sufficient conditions for all the bad events ei being simultaneously avoided. And again, as is very well known, the basic symmetric version of the local lemma says that if there is for every I, if there is a uniform bound p on the probability of this bad event happening, and if in the dependency graph each ei has degree at most d, then something like pd less than or equal to 1 is sufficient. Technically you need an e here, right? And later we'll see why this +1, there was some very nice work of Shearer, and we'll briefly talk about it, and in particular it shows that this +1 is not needed. But essentially this is a tight condition, right? So there's not much more, it appears like there's not much more one can say. And for instance, one of the standard applications is if you have a k-sat formula, where by k-sat, let's assume that every clause has at least k literals. Then if you do a random assignment, the probability that any particular clause fails is 2 to the minus k, and therefore if each clause overlaps at most something like 2 to the k over e other clauses, then actually there exists, the formula is satisfiable. The question is how to efficiently find a good assignment, right? So how to make this thing constructive basically.
So even before, just for people who have never seen it, the amazing thing is that this condition on P and D does not depend on the number of variables n. It
Yes.
doesn't matter at all how many variables or clauses, just that this constant independence.
Yeah, like Avi says, basically, yeah, there's a scale-free condition. So it's however large the formula is. I mean, so how would you normally prove this? If you try a union bound, for instance, then if there are m clauses, you'll need that m times 2 to the minus k is smaller than 1. So k has to be at least log m. But here you may, even if k equals 3, you get some or k equals say 5, you get some non-trivial condition, right? It's a completely local condition, as Avi said, independent of this. In particular, please note the distinction between n and m. This will be important. So yeah. So how can we efficiently find a satisfying assignment if the sufficient condition is true, right? So Moser and Tardos, so again, this is called the variable version of the local lemma. The local lemma itself is a little more general. It doesn't require that your bad events be driven by independent random variables like this, but essentially this captures most known applications, right? So here is the amazing Moser Tardos algorithm for.
Can you go back? I want to slow you down again. When you say algorithm to find good assignment, what Aravind means is a probabilistic algorithm to find good assignment. It's not completely obvious, even though it's a probabilistic procedure, because it's greater than zero. The probability that all events are avoided is exponentially small.
Yeah.
And it's necessarily exponentially small.
Okay, that's an excellent point. Maybe I can use the board to just demonstrate what Avi just said. So suppose you have so suppose you have this dependency graph. You have m nodes, one corresponding to each bad event. Each has probability p. The point is, if the max degree is less than or equal to d, then there exists an independent set I of size m over d plus 1, right? You have an undirected graph on m nodes, max degree is d, so you have an independent set of size m over d plus 1. The probability that that you manage to avoid the bad events just in the independent set is something like this, right? So the probability that all the bad events in I are avoided, right? Probability that all EI in I avoided is something like this, right? So this is approximately exponentially m over dp, right? I'm sorry, mp over d, excuse me, mp over d, which basically is like m over d squared, right? So even the probability that you avoid everybody in your independent set can be as small as exponential in m over d squared. And we typically think of d as say constant or polylog or something. So this can be truly very small. So the probability that you avoid all the bad events is only smaller than this. So like Avi points out, the non-trivial issue here is that the local lemma truly only guarantees the presence of a needle in a haystack. This probability is inherently small, basically. So in particular, yeah, so there is no, typically you don't get a randomized polynomial time algorithm by just for example, sampling, constructing a random assignment, right? So we want a randomized polynomial time algorithm, right? How to find such a thing? So we'll now look at Moser and Tardos's amazing, algorithm for this, and it's in this general setting, right? In the general variable setting. It's perhaps the simplest algorithm one can think of. I think, in fact, after Beck's early work on algorithmic versions of the local lemma, I think Alon and Reed, Noga Alon and Bruce Reed actually tried something like the following they mentioned, but there wasn't success then, but I believe, and then Moser and Tardos completed the picture. Here is their truly simple algorithm. So initially sample all the variables xi from their distributions, of course independently, right? And while at least one bad event is still true, pick one of them arbitrarily and just resample its variables, right? So suppose EI depends on x1, x5 and x8, just resample them independently from their marginals, that's it, right? This is all the algorithms, right? Perhaps the most natural algorithm, and we'll see actually there's a simple proof for this, and like I said, I hope to demystify part of it at least, right? So their main theorem is, in fact, there's some slight qualification you have to make here, but this is essentially true. The point is the number of iterations, the number of resamplings, the expected number is at most O of m. Right?
I have a question. Couldn't we do a simpler algorithm, something like in favor of conditional expectations? Just say, in the case of the case set, we can just enumerate over all possible assignments to the first clause. We know that at least one of them, for at least one of those assignments, there will be the remaining formula will satisfy this condition.
Okay.
So we can repeat it.
Okay, excellent. So the question is, why can't we do something like the method of conditional probabilities? The point is, if you look at the proof of the local lemma, so if you want to run the method of conditional expectations, you have to actually look at the proof and set the variables one by one, right? If you look at the proof, it looks like a continued fraction, and if you unfold it, the length of the algebraic expression you will get is exponential basically. So to run the method of conditional probabilities, to calculate each conditional probability at least naively by just looking at what expression the local lemma gives will take you exponential time.
No, I'm not suggesting doing conditional expectations as is, but rather, I mean, I don't want to compute the conditional expectation, just to do the following. I take, say, one variable and I try to either set it to true or to false. Now, after I set it, I check whether the condition of the lemma of the LLL still holds.
Mm-hmm.
If it still does, I know that I can continue with this fixed assignment and go and continue on.
Yeah, so unfortunately you can construct instances where for a variable whichever of the two branches you try, the condition of the local lemma is violated.
Oh, right.
Because 2 to the minus k will shrink, right, to 2 to the, yeah, that's the problem, yeah. The usual sub or super additivity that you require will not be true, basically.
I see.
Not on the condition, on the probability, of course, but you cannot.
Yeah. So, this is their main theorem, right? It's like I said, you have to qualify this a little bit, but essentially think about it like this, right? But actually there are two issues here. I mean, so this already, certainly for KSAT and, several other applications of the local lemma, this is sufficient, right? This gives you a genuine randomized polynomial time algorithm, right? But actually there are two subtle issues, that sort of stop this from being universally applicable. One is actually, if, what do we mean by a randomized polynomial time algorithm? Notice that the output size of this problem is just n, right? So if you recall, the sort of underlying, what you want as an output of your algorithm is one value for each of these variables that certifies that all the bad events are avoided, right? So the output size is really proportional to n, basically, not m. M could even be exponentially large in n, right? So suppose these bad events are somehow implicitly specified, if you there are applications where you just want something polynomial in n, and that need not be the case, at least naively from Moser Tardos, it could depend linearly in m. So actually that turns out to be less important. So the bigger issue is, what if this thing, you have a current assignment for the variables, either certify that this assignment make sure that none of the EIs is true, or if that is not the case, pick one EI that is currently true. That actually can be an NP-complete problem.
Well, I mean, not if it's constant size in most applications. In most
Yeah.
applications, the functions are of constant number of variables.
Yeah, in most applications that's true, but not all. So for example, there is this stuff called non-repetitive graph coloring, and and also, yeah, so that's one thing. Also, there has been a lot of work in the last 10 years on what is called the Santa Claus problem, or max-min fair allocation. I can tell you the definition if you're interested in. So for example, Feige came up with a non-constructive argument for this. What do I mean by that? So he constructed, so that's an integer programming problem. He constructed what is called a configuration linear program, configuration LP for it, and that actually can be solved in polynomial time. It's exponentially large. It can be solved in polynomial time. He showed that there exists an integral solution with value of constant times the value of the LP, right? Using the LLL basically, right? But there are exponentially many, and they're not constant sized, for instance, right? So there are cases where, again, this is lesser of the issues, and this is the sort of more thorny issue, right? So how do we handle these? So in this work with Heupler and Shaha, we actually showed that both of these can be handled in an easy way if you allow a little bit of slack in the LLL condition, right? But please is any questions about the algorithm itself? Just the most natural algorithm you can think of, and keep the distinction between n and m in mind, right? Yeah, so our first result, actually the second result I personally like even more. The first result says the following. So recall that, that both by allowing a small slack, so recall that the general asymmetric version of the local lemma says the following. So if for each bad event you can assign a real xi between 0 and 1, such that this condition is true. For every bad event, the probability that it happens is I, the probability it happens is at most xi times the product over all the neighboring events j of 1 minus xj. If there exists such a collection of reals, then the general version of the local lemma says that with positive probability you can avoid all of these. So what we show is that if you can allow a tiny slack here, if there is for any positive constant epsilon you can actually guarantee this, then in fact and I'll give you a very very brief proof of, or very brief idea of how this works. What we show is that in fact even if both conditions of the local lemma are true and so on, we show that you can essentially drop almost all of these bad events and just focus on a polynomial in n number of the bad events and just apply Moser Tardos on them. Okay. So there exists, as of your bad events, you can easily identify an explicit subset of size only polynomial in n and just run Moser Tardos on this. And since this is an explicit polynomial sized collection of bad events, usually checking finding a bad event and so on is quite easy, right? So essentially with this, if you allow the slack, this makes most known direct applications of the local lemma algorithmic, except for what is called the lopsided LLL, which I'll come to at the very end of the talk, right? So this is our and I'll very briefly show you the primary idea that drives this. This is our first result. Like I said, the second result is perhaps of some more interest, and in particular the applications I mentioned in the previous thing, like maximum fair allocation, all these can be made constructive with a slightly larger constant. Because of this blow up, they can all be made constructive. Right? So actually, yeah, I find this somewhat more interesting. Before I come to that, let me say what the main driving force behind the two results is. It is this, and this again follows fairly easily from Moser Tardos's work. It says the following. It says that basically the output distribution of Moser Tardos also has some enough randomness, is quite interesting. It not just make sure that all the EI are avoided, but in fact this output distribution D of Moser Tardos says the following. Take any function, it need not be any one of the given EI, take any Boolean function A that's some function of the underlying independent random variables, then the probability that it happens in the end when Moser Tardos terminates is not much more than its unconditional probability. It's at most the unconditional probability of A divided by all the events Ej that A depends on of 1 minus xj. And what are these xj's? These are these numbers from this condition, right? So your LLL application requires something like this. If it actually satisfies this, or a stronger version like this, take these x values and you can actually show for any Boolean function of the xj's that in the end it's the probability that it happens in the output of Moser Tardos is actually not much more than its unconditional probability. The proof is by this witness tree argument that Moser Tardos come up with, which I'll focus on. Here is an interesting corollary. This is something I personally like a lot, right? Now if you look at SAT, right, if you are just teaching the elementary probabilistic method, if you're looking at KSAT, one can say two things, right? Like we saw before, if the dependency D is good enough, if D is less than or equal to 2 to the k over e minus 1, then that's great, the formula is satisfiable, right? But if D is even a little bit more than this, we say all bets are off, we cannot say anything, and just that the expected number of violated clauses is m times 2 to the minus k. We just apply the linearity of expectation, right? So so we say that, for example, 1 minus 2 to the minus k fraction of the clauses are satisfiable and so on, right? So if D goes even a little bit above this, essentially nothing is known in general, right? And the same you can say for general applications of the local lemma. If D is a little more than this, just apply the linearity of expectation, but can we interpolate between these two, right? And that's what we show actually as a corollary of this. If D, so recall that the local lemma requires something like D is something like 1 over EP, right, where P is the probability of any one of the bad events, right? Let's parameterize as D is 1 over P times alpha, where alpha is bigger than 1, right? What can we say here? Can we interpolate between the two extremes? We actually show that that is the case, that if D is of this form approximately, where alpha is larger than 1, unfortunately the range for alpha one can show is provably small. Alpha can only lie between 1 and E. if alpha goes more than E, right, basically if, in other words, if D is more than 1 over P, in general there is nothing you can do beyond the linearity of expectation, right. So the range for alpha is narrow, but we do what we can, and what we show is that the expected number of bad events that happen is something like this, right. But the main point to note is that this is the correct interpolation. When alpha is 1, this is 0, so this recovers the LLL, and when alpha is E, this quantity is 1 in parentheses, so you get the linearity of expectation, and between the two we interpolate, right. And to our knowledge this is new even non-constructively, but of course because of Moser Tardos we are also able to guarantee this constructively. In other words, in randomized polynomial time you can construct an assignment for the variables in which the expected number of violated events is MP, which is the original expectation times this quantity which is smaller than 1, as long as alpha is in its domain, which is 1 to E, right. So for example, for maxat you can still say something if D goes a little bit above so what the LLL requires. Okay. So what is this witness tree stuff? This is the main thing behind Moser Tardos. Let me talk about that, and then I'll talk about further extensions that we have been working on in the last few years. So it's a really nice proof, and very so here is the idea. Okay. So
you are actually going to prove the theorem you stated? Are you proving this, or you just prove that you find the satisfying design?
So I'm not going to prove this. I'm actually going to show Moser Tardos and show how, because Moser Tardos, it is a short proof, but still there is this branching process and so on, which I think is not necessary. It's a very you can think of it as just a set of recurrences. That's all, a witness tree and a simple set of recurrences. That's it, right? So I'd like to I think this demystifies MT a little bit. So here is the idea, right? So again, recall what their algorithm is. Let me go back to it. So
When you say recall, I don't know that everybody has seen it. So
I see. Okay. So this is MT, right? Right. So you want to bound the number of iterations basically. So you do an initial sampling and then you keep doing resamplings, right? And question is, what is the expected number of resamplings, right? So we'll count time as the number of iterations. So so basically we want, the proof idea is really this: you want to find a reason for a large number of resamplings, right? In fact, so at time 0 you do the initial sampling, at time 1 the first resampling, and so on, right? At every time actually you will construct a witness tree. So at time t, suppose the t3 sampling was for event EI, right? We are going to construct a tree rooted at EI that gives some partial explanation for why you had to go all this way, and in particular you had to resample EI as your tth resampling, right? So you're going to construct this witness tree going back in time, starting from t. So at time, so you go back in time. At time t you construct a single node with root EI, and now suppose you have come down all the way inductively to time t prime less than t, and at time t prime suppose you resampled in your algorithm because of you resampled for event EO. Okay. Now there are two cases. The trivial cases that.
Just a second. What are the branching? The branching are the actual assignment. What is labeling the edges?
Yeah, it's very important that the edges are unlabeled actually. It's an unlabeled tree. The nodes will be labeled with bad events. If you label the edges, the number of possibilities becomes too large.
So okay, but what do the children of EI mean?
Okay, so yes, okay, so let's look at the inductive rule and then that will show you. So the inductive rule is, so again at time t you constructed a single the root, and suppose you come down up to t prime, which is smaller than t, and suppose the MT in this particular run of MT resampled at time t prime because of event EO, right? There are two cases. The trivial cases, EO is not a neighbor in the dependency graph of anybody you have in the tree so far, right? In that case you just you ignore it and go to t prime minus 1, right? So that's not going to be the typical case. The interesting case is that EO is a neighbor in the dependency graph of somebody in the tree that you have constructed so far, in which case you make it a child of the deepest node of which it is a neighbor in the dependency graph, right? So again, the interesting case is when EO does have some neighbor here in the tree that you have constructed so far, a neighbor in the dependency graph. So suppose, for example, it's a neighbor of ek and a neighbor of ei. Since k is deeper in this tree than ei, you make this e0 a child of ek, right? So this gives a partial explanation. So to go back to Avi's question, this basically says that, for example, these three children of ei, they have to satisfy the condition that ea, et, and ec are all neighbors of ei in the dependency graph. In other words, for example, ea shares some variables with ei, et shares some variables with ei, and ec also does, right? So this edge suggests, not necessarily with complete certainty, but suggests that in resampling for ea, you resample some variables, right, which also impact ei, right? So the reason why ei, this suggests, again not with certainty, but suggests that the reason why you had to resample ei is perhaps this resampling of ea screwed up the variables on which ei depends, and therefore you had to resample ei, right? So a necessary condition in this tree is that, and we'll see one other really useful necessary condition. The necessary condition in this tree is that any parent and child have to be neighbors of each other in the dependency graph, right? But then the rule for, and you'll see we'll see a very simple, very nice consequence of this rule of making as you go back in time, as you make a node a child of the deepest node in the current tree, let's see a simple consequence of it.
So can I ask a question about this? We know we sampled in time t minus 1. ei we sampled at time t. And it happened because we sampled some other thing in time t minus 1. So why are there more than one?
I see. So
just because they came
from below,
from
different times, yeah.
So it's not really
Yeah, like Avi says, so of course these ea, this t is bad notation. So these nodes, of course you only resample one event at any time. So these guys were sampled at different times earlier than t, right? So a very important thing to note is that the edges are unlabeled basically. So you really, the tree representation is pretty sparse, so you can count the number fairly, compactly, right? So notice, here is the only property that we'll need. The only property we'll need is note that if you look at any level of this tree, they have to form an independent set in the dependency graph, right? Because if not, if these two guys were related, well, one of them came earlier in the resampling, why was it at this level and why not at a lower level, right? Because of this deepest neighbor property, right? So this is the only thing we'll require. The only two properties we'll require are any parent and child are neighbors in the dependency graph, and every level of the tree is an independent set in the dependency graph, right? No, you don't. Yeah, very good. We don't need that because that will be useful in the next slide or so, right? So this is the thing. Now, actually,
tree at time t has t nodes.
Not necessarily, because you may have dropped some guys, right? Some e0 at time t prime. If it had no neighbor in this tree, you'll just at most t. Yeah. So so you're going to do this for every t, not just the last step, but imagine constructing one tree at time 1, one tree at time 2. Yeah, the tree at time t will have at most t nodes, right? It looks like this basically, right? So it doesn't have any other edge labeling or other information, and notice that there could be multiple copies of a node and so on, right? So this is possible, right? So now, here is the key. I think the key contribution of Moser Tardos is the following: fix any particular tree t. Okay, again without any edge labelings, and where you don't care about the left to right ordering in any particular level. Just fix a tree with a rooted tree, right? The really nice idea is it's a very simple argument. They call it a coupling argument. Is the probability that this fixed t appears in your list of witness trees. Please recall that you construct one tree at time 1, one at time 2, one at time 3, and so on. The probability that this fixed tree appears ever in your list is exactly the product of the probabilities of the nodes in the tree respecting multiplicity. So if node E5 appears 10 times, you will take it to the power of 10, right? Right. This is and here is a sort of one slide proof of it, right? And this, I think, is their key contribution, which is what holds in various further extensions of Moser Tardos also. Okay, so keep this in mind, and then this, so the weight of a tree, of a fixed tree, is just the product of the probabilities of the nodes in it, respecting multiplicities. So the idea is the following, right? So let's prove this. So instead of resampling on the fly, imagine that you created an infinite table initially where for x1 you sampled it infinitely many times from its distribution and so on, right? So suppose you imagine that you constructed a table like this, right? So initially you have a pointer for the initial copy of each variable, and every time you resample you advance the pointer. For example, if you're currently here and you resampled x2, you instead of resampling it on the fly, take this value and move the pointer forward. So imagine that there is this table, right? Now to evaluate this probability, let's go bottom up. We'll do a breadth first search. So we'll do a level by level analysis, but go bottom up, right? Okay, so let's take this simple tree, okay? Just a 3-node tree where EI depends on these 3 variables, EJ on these 3, and EK on these 3. Notice that EI and EJ are neighbors because of their overlap. For example, in x1 and x2, EI and EK are neighbors, they overlap in x3, and in particular these guys don't overlap, their subsets are disjoint, right? Now let's go bottom up, right? So why, just look at this tree. You don't know, I mean, you don't have any other identifying information like at which time they were resampled and so on, but actually you can completely reconstruct that, because look at this EJ, which copies of x1, x2 and x4 from this table made this EJ happen, right? They have to be this copy of x1, the first copy of x2 and the first copy of x4, right? Because if not, if some earlier, for some later copy, such a node would have been a descendant, or at least somewhere below the tree here, right? Below in the tree, right? So this particular node was triggered exactly because of these 3 copies of x1, x2 and x4. So the probability of that is the probability of EI, right? Of EJ, right? Similarly, for x3 and x5, this event was triggered because of this copy of x3 and this copy of x5, right? So you move the pointers for all of them, x1, x2, x3, x4, x5 forward. When you come to, therefore, to EI, you know exactly that EI was triggered because of the second sample version of x1, second of x2, and second of x3, and so on, right? So if you basically, because every, if you think about this a little bit, essentially because every level is an independent set, it doesn't matter in which order you process these guys, left to right, right? There's no left to right information, you can process them in any order, and essentially when you come to any node in the tree, you can precisely say, if this guy depends on x1, x4 and x5, you can say that, oh, it happened because of this copy of x1, this copy of x4 and this copy of x5, right? So the probability of that is of course the probability of that event, right? And these variables will never overlap, these copies will never overlap, so it's just the product.
So it's not even simpler than this, just because whenever you are fixing an event, resampling for an event, you use fresh randomness.
That's true.
Basically,
that's basically it, but you can't just take the product because you don't know which copy made it happen, right? And it's a little subtle because so I see. So obvious question is, why do we even need all this? Because if you look at this tree, but for instance, if these guys, if the tree construction was such that these guys were also neighbors, if that was possible, right? Then it is true that they were sampled from different copies, but then you have to do a bound over, something like union bound over, either this happened the first time and this happened second, or this the second and that the first, and so on, right? So you'll have to sort of do more than this basically. So I mean, so yeah, really you're just using the fact that in every level you have an independent set, and you do this bottom up BFS basically, right? So this is the key lemma of Moser Tardos, right? Once you do this, well, it's easy, just a union bound. I mean, this is where, so this is their key lemma. They call it a coupling argument because they couple it with this table, right? But after this, they show a branching process, which I think is a little bit of a red herring. I mean, the thing can now be analyzed very explicitly, right? Just using recurrences basically, and a fixed point of this system of recurrences. Why is this? Once you have this thing on the probability that this particular tree ever occurs, right? Notice at least one thing, right? If, for example, if EI is resampled some k times, right, then the number of trees with root equal to k, I'm sorry, with root equal to ei has to be k basically, right. You know, so suppose it was resampled at some time, there will be some tree. If it was resampled at some later time, the tree that you get cannot be the same as this. It has to be bigger than this, right. So if as you run your algorithm, if a particular event ei was resampled k times, then if you look at your list of trees, the number of trees with root equal to ei has to be k basically, right. So the expected number of iterations overall is simply the sum over all possible trees t of the probability that it happens, right, just the linearity of expectation. So basically once you have the probability that a particular witness tree occurs, the expected number of iterations is simply the sum over all possible trees t of this quantity. Basically because, you know, just think about it this way, you know, what is the expected number of times ei is resampled in your algorithm? It's the expected number of times, you know, it's you get a tree with root equal to ei, right, which is the sum over all possible witness trees with root ei of the probability that it appears in your list, which is this, right. So all we are really interested in is the sum over all possible witness trees of, so now it's just you know, just a combinatorial problem, which is what they solve using a branching process, but I think it can be, you know, sort of thought of in a simpler way. It is just this. So we are really interested in this sum, the sum over all possible witness trees of of the product of all the ei in t of the probability of ei, right. So this is all you need really, right. Now let me point out, you know, so there is a simple recurrence you can write for these. So basically suppose so let's okay, so suppose you restrict to trees with root ei, right. So let f of I be the sum over all trees with root ei of this, right. Now recursively, how does such a tree look? Yes. So basically the point is its children all have to be in the tree, all have to be its neighbors, right. So if you want to calculate the sum over all eis like this, well, how do you sum over all of these? Well, you know that the root is ei, right, and its children are some subset of its children. The children in the, I'm sorry, are some subset of its neighbors. And in fact, the only thing we'll use now, and we'll see later that this can be sharpened a little bit, you know, we know that this has to be an independent set, right. So a trivial consequence of that is that no node can be repeated twice here, right, just a trivial consequence, right. We don't even, suppose we don't even use anything more than that, you know, there is this ei, its children in the tree will be some subset of its neighbors in the graph, and since these guys form an independent set, no node can be repeated, that's all. That's the only thing we need here. Then recursively, this, so suppose let's say we fix this subset, say j1, j2, j3, j4, then recursively you sum over all possible trees rooted at j1 and so on, right. So really then the recurrence you get is, and notice that one of the children can be ei itself, right. So the simple recurrence you get is f of I is, well, remember you take the product of all the nodes here, so you certainly get the product of ei here, right, times the product over all j, except that j also can be equal to I. So j is in I union the neighbors of I in the dependency graph of 1 plus f of j, right. Basically this 1 corresponds to not choosing j, and f of j corresponds to choosing j, right. So all the 2 to the, if it has t neighbors, also add I to the neighbors, so 2 to the t plus 1, you get all the 2 to the t plus 1 things. So this choice corresponds to not choosing j as a child, and this corresponds to choosing j, that's it, right. So you just need to show that this system has a fixed point, right, that's all it is basically, right. So, but of course you know that just because a fixed point exists, that doesn't mean that the system should converge. So you just have to be a little careful. In this fixed point, let's say you parameterize by the depth of these trees. Suppose you're counting over all trees of depth at most d, you get something like this, right? So d minus 1. So just by induction on d, if you apply, so the nice thing is, if you look at it this way, yeah, in fact what you get is exactly one simple sufficient condition for this to for this system to be satisfied is basically this. So like I said, this you get this recurrence, right? Then in fact you can explicitly recall so far, in fact, so in Moser Tardos they assume the LLL hypothesis and then show a branching process, right? But here actually in the simple alternative, you don't need to assume the LLL hypothesis. Recall the LLL hypothesis has something like this, right? So here you can actually explicitly say that if there exist xi's between 0 and 1, suppose such that this is true, right, then this system has a finite solution, this system of recurrences. So therefore actually you recover the LLL condition, right, as a consequence of Moser Tardos, rather than assume the LLL condition and prove that it converges, right? But so I think this is a slightly simpler way of thinking about Moser Tardos. Again, just use this very important property and sum over all possible witness trees of this thing, and you see that in fact this is sufficient.
So you show it's like if and only if the condition, the initial condition satisfies if and only if this thing converges and vice versa.
Very good, very good. That's a good question. It's not actually if and only if, because after the local lemma was originally developed, Joel Spencer had a question. So recall that in the symmetric version of the local lemma, you require something like this, right? So his question was whether this constant is tight. Okay. So Shearer actually showed that the constant is tight in a very nice paper on that's been used a fair bit in statistical physics by Alan Sokal and so on, Scott and Sokal. But he went further, right? Shearer considered this very general problem, right? And in fact, he shows that this +1 is also not necessary. Assuming that d is non-zero, this can be removed, right? But he actually shows that you can go beyond the local lemma, right? So he considers a very general case. Suppose I give you an undirected graph, right, with each node corresponding to a bad event, right? I don't tell you how these bad events are generated, but I just give you a graph, right? And
Something about sigma algebra or about some sigma algebra being closed or something like this, right?
just certain independent set polynomials always being positive, right? So his question is the following. Consider the following so suppose there is an m vertex graph. M is the number of bad events, right? What is the following m dimensional body, right? His question is, so the graph is given, right? So this graph G is fixed, right? And then his question is the following. So this vertex I, vertex J. So so Pi, yeah. So his question is, consider the following body, right? So these edges in the graph are supposed to mean dependencies as usual, right? His question is, what is the set of all probabilities you can assign, one to each node, right? So consider this body. Shearer of G is the set of all P1 through Pm, right? Such that no matter what bad events you associate with each event, with each node in the graph, right? For all E1 through Em, with the following conditions: the probability of Ei is Pi, and G is the dependency graph of the Eis, right? For suppose you can, you're given this graph, right? Take all possible probabilities you can respectively assign to the bad events, right? And you have complete freedom in designing these bad events as long as the dependency graph is this. Now the Pi should, if for all this, what you need is that the probability of avoiding all the bad events is positive, right? So consider this body, right? So he gave a characterization of this body based on independent set polynomials. Okay. So given a graph with m vertices, consider this body in M space. It basically says no matter how you design a bad event, one for each node, as long as G is the dependency graph of these and Pi is the probability of EI, no matter what, otherwise no matter what these bad events are, if you are given this, so for example, as a trivial, sorry? I don't even think it's a convex body. Yeah. Yeah. So for example, if it's a complete, if it's an empty graph, the only thing you require is that each Pi is smaller than 1, right? If it's an empty graph, they're all independent, and the only thing you require is they're smaller than 1. If it's a complete graph, the only thing you can do is the union bound, so it corresponds to the sum of the Pi's being less than or equal to 1, but otherwise it's a rich structure, right? So this is not actually, it's an excellent question. So this is not necessarily an if and only if condition, and in fact, yeah. No, Scherer's information theoretic inequality is different. Yeah. Yeah. So, but then actually that's a very good point. But then there is an even simpler answer to your question why this is not a. In fact, this corresponds to some improvements that were made in the local lemma, right? Now, if you look at this argument again, right, this is not tight because actually you cannot. So here you did not exploit the fact that the children have to be an independent set, right? So obviously, if you do it, you can get some improvement. In fact, here is a simple improvement you can make. Let's just do a case analysis, simple case analysis. If EI is, if this node EI is replicated as a child, right, then in fact there can be no other children, right? Because if this was EI and these other guys were neighbors of EI, then there will be edges between these, right? So there are two cases. Either EI is a child, if you look at this root node, either it has EI as a child, in which case that child has to be a singleton, or all the children have to be different from EI. If you just do that case analysis, you already get some improvements. In particular, you get EPD less than or equal to 1 if D is non-zero. Yeah, that's possible. It's possible. Yeah. So here is this interesting question. So can you really consider this problem in a graph, right? So you just want to construct rooted trees with two conditions. One is the parent-child relations in the tree have to satisfy the neighbor relation in the graph, and every level has to be an independent set in the graph, right? How many, and then the weight of the tree is the product of the probabilities. What is the total weight? So this is an enumeration problem. There doesn't seem to be a clean solution to this if the graph is arbitrary. But there are some simple things you can do like this. In fact, Wesley Pegden made this observation. But there is more to say about Scherer. I'll say a little more. Scherer's stuff is great. So yeah, you can make some further improvements. And this is not our work. Other people have done this. So in particular, for small k, the local lemma is not tight. You can get some for asymptotically for large k, the local lemma is tight, but not for small k. Okay, so now let's actually. Let's actually go a little bit beyond the Moser Tardos thing. So like I said, we think that the Moser Tardos procedure itself is of independent interest. I think it should be viewed as something more than an algorithmic version of the local lemma. So this joint work with my student David Harris, we had some papers on it last year, right? So consider the following. This is actually a simple universal definition. So suppose you have a constraint satisfaction problem with n variables. The ith variable takes values in some set ai. Then of course let xij be the indicator for I taking on the jth value from ai. Then you have this, of course, the assignment constraint. And suppose, this is without loss of generality for any assignment, for any constraint satisfaction problem. Let v be the set of all the variables, right? And then you have one bad event for each k running from 1 to m. The constraint, the complement of the constraint corresponds the kth constraint, and this bad event is that some particular increasing function bk, it's some function only of some subset, and without loss of generality you can assume it's increasing, and this bad event is that this particular increasing function is true. In other words, your constraints are all decreasing Boolean constraints, right? And you want sufficient conditions under which this this integer program is satisfiable. This is actually general because there is a simple reason. I mean, there's no.
But, if you want the function to be monotone, you
Yeah.
allow monotone or anti-monotone in every variable. Because otherwise,
The reason is you because of this you have xi0 and xi1, right? So it's trivially, I mean, there's nothing, I mean, so I mean it could be increasing in xi0 basically. One constraint could be increasing in xi0, another in xi1 for trivial reasons. That's not a problem.
if one closes x1 down,
Yeah, because of the assign, one constraint, for example, for variable I, you'll have xi0 and xi1. One of them could be increasing in xi0, the other in xi1. So it's trivially. I'm not saying anything interesting here. Yeah. So I mean, there's nothing interesting here, right? So this is a general definition. So here is actually an interesting application of this, and I have a nice open problem for you, starting from Penny Haxel's work, right? So this was actually introduced by Lovasz, Tardos, and Semeridi, and it has several applications. It's called the independent transversals problem, right? So you have an undirected graph with max degree delta, and suppose an adversary partitions the vertices into blocks, right? In such a yeah. So his his or her main constraint is that they cannot make any block too small, right? So they have to make each block at least somewhat large, but otherwise they can do it arbitrarily, right? So this problem, called the independent transversals problem, is the following, right? And so you are given this graph, and an adversary comes and partitions the vertices into blocks, each of size, let's say, exactly b, right? Otherwise, but the adversary can do anything, right? What you want is a transversal. Recall that a transversal means a choice of one vertex from each block, right? And furthermore, it should be an independent set, right? So that's the independent transversals problems. That's what they considered mainly, and then we'll see some work by. This is by. Excuse me, I didn't say who the. This is by Lowe and Sudakov, right? Sudakov and Poshin Lowe. His ex-student showed this, right? Okay. So consider the following problem. You first want a transversal. So think of this. Think of one variable in your CSP corresponding to each block. This variable can take either this value or this value or this, and so on. So in other words, you want to pick one of these values or one of these vertices, for exactly one from each block, and then you have some decreasing constraint on these. For example, that there is no clique of size greater than or equal to s in the subset of the vertices that you pick, right? Again, you pick one vertex from each block, and the chosen vertices, in their induced subgraph, the maximum clique size should be at most s minus 1, right? Consider this problem. The case s equal to 2 is very well studied. So in other words, you want one vertex from each, so that the vertices you pick form an independent, form an independent set, right? So the main question is, what is the so what is the minimum size b, right, such that no matter what the adversary does, you can always construct such a good transversal, right? Like I said, the case s equal to 2 is very well studied. There is a very interesting open problem here. So Penny Haxel, so Noga alone using the local lemma showed that b equals 2e times delta suffices, right? And Haxel showed non-constructively that this is that in fact it's enough if each block is of size at least 2 delta, you can always find an independent transversal, right? This result is not yet algorithmic, right? And this 2 delta is tight in a very strong sense. You cannot even replace it by 2 delta minus 1, right? It's truly tight. This is not yet algorithmic. Her proof is topological, right? So so more generally for general S, what is known? So Szabo and Tardos show that. So think if S is large, they show approximately delta over S, lower bound on B, right? And the upper bound, like I said, this is by Lowe and Sudakov. I forgot to mention this. They lift the result of Haxel and show non-constructively that that this suffices, that b less than or equal to this suffices. So again, for large delta, this is approximately twice the lower bound. So we showed that in fact the lower bound is asymptotically tight. One of the things in particular we show is that what we show is that the lower bound is tight, right, for large S, right? But what is the proof idea? The proof idea is simple. So again, like Avi mentioned early on, right, what is the natural approach to these constraint satisfaction problems? Of course, given these fractional values xij, just choose one of them randomly, and if you just do a union bound, then you want the probability of the typical bad event to be much smaller, which is too much to ask. And on the other hand, you can do the local lemma stuff, which is you choose one value randomly for every variable I with this marginal, and do it independently for the different variables, right, independently, and then just apply the local lemma, right. So if no variable appears in too many constraints, then the local lemma sort of thing can hold, but and you can apply Moser Tardos to make it constructive, but our main idea is the following, is of partial resampling in the Moser Tardos context. Remember that each bad event EI is defined some subset of the variables, and in Moser Tardos, if this is currently true, you will resample all these, right. The question is why should you resample all of it, right. So our main idea is you a priori for every bad event EI, recall that it depends on some subset Si of the variables, we will construct some distribution Di on subsets of Si, and whenever you need to resample for EI, you choose a subset first from the distribution Di and only resample the subset, right. So hopefully this will prune the dependencies, prune the space of trees you have to do a union bound over, and so on. So for example, in this problem of constructing good transversals, right, if currently a bad event holds, if there is a clique of size S, you actually just choose the correct sweet spot is like square root S, you randomly resample a square root S sized subset of it, then one of the consequences you get is in fact that this lower bound is tight for transversals that avoid cliques of size S. So asymptotically the lower bound is tight, right. But like I said, perhaps the most interesting case is S equals 2, right. So Alon's proof, so what is known, so again let's look at this. This is a very interesting open problem. So you want an independent transversal, so you want to pick one vertex from each block so that you get an independent set. So Alon's proof, which is a direct local lemma based proof, shows that if the size B of every block is at least 2E delta, delta is the max degree, then we are okay, and by Moser Tardos you can make it constructive also, right. On the other hand, Haxel shows that 2 delta is the optimal value. Now using these things of pruning the witness trees and so on, you can actually show a little bit better, B greater than or equal to 4 delta suffices algorithmically, right. But non-algorithmically the best known is 2 delta, and that's optimal, and it's not yet known how to do better than 4 delta. Yeah. So the it shrinks.
So if it's subsets of variables, whether they intersect as opposed to the
original, yeah. So that's a very interesting open problem. Whether you can improve from so algorithmically the best known for this classical problem is 4 delta. Whether you can push it towards 2 delta is interesting. Let me show a couple of other quick applications. So there is this classic work of Lensthrush, Moise, and Tardos, and Azar and his student Epstein about 10 years ago, they considered a more general multidimensional scheduling problem. So essentially, suppose there are, again, there are n jobs, each has to be assigned to one of m machines, right? And suppose the load on a machine is not just the processing time, but other dimensions, and let's say there are d dimensions in total. In particular, suppose if you choose to assign job j to machine I, then in dimension k, suppose it adds some Pijk where these numbers are all given to you, right? And the standard question is, is given a vector T1 through Td, is there an assignment of the jobs to the machines, where in the dth dimension for little d, the load on any machine is at most Td. The classic work of Lensthrush, Moise, and Tardos is when d equals 1, when uppercase d equals 1. In that case, they show a 2 approximation. This is called the scheduling on unrelated parallel machines. It's still open whether you can improve that. Azar and Epstein show that in fact there you can get d plus 1, and one can improve this to something like this. So using this partial resampling idea. Only for the integrality gap. So the scheduling problem of Lensthrush, Moise, and Tardos, maybe I should mention that it's a really interesting open problem. It's maybe one of the sort of most fundamental open questions in approximation algorithms to my mind. So let me just so that's only for the integrality gap. So here is what is known. So this is Lenz-Tardos from the late 1980s, right? So you have some n jobs, m machines. You want to assign every job to one machine. So you have the jobs, you have the machines, and if you assign job j to machine I, that imposes a load of Pij on machine I, and the total load is additive, right? And you want to minimize, you want to do an assignment that minimizes the max load, right? So for this, they give a 2 approximation, right? And they show using non-PCP, of course, because this was early 1980s, they show that 1.5 is not possible, right? But this is the best known even today. There are some special cases where 1.75 can be done, and significant special cases you can do p-TASes for, but this is what they show is that the integrality gap of the natural LP is like 2 minus 1 over n. So, but the d-dimensional version is this, so one can do get some improvements there. As a final application, let me consider the seminal Leighton-Max-Rao result, right? So you are given a packet routing problem, right, where each packet also has its routing path. So a packet I has to go from Si to Ti using this given path, right? And you want to do the packet scheduling. So so nodes can queue packets, and an edge can, let's assume that time is discrete, and an edge can only take one packet at a time and move it along. You want to minimize the time by which the last packet is delivered. The amazing result of Leighton, Max, and Rao using making sophisticated use of the LLL is the following: that a certain natural lower bound is in fact optimal to within a constant, basically. So the 2 simple lower bounds on the delivery time or make span are, this is the easiest lower bound. Easy lower bound is the maximum length of any given routing path. You need at least that much time to deliver the packet. The other is the maximum congestion on any edge, the maximum number of given routing paths that use that particular edge. Since an edge can only ship one packet at a time, you need at least that many time steps total. So these 2 are simple lower bounds on opt, right? So you have this. So LMR, their constant was very large, and there's been steady progress, and what we are able to show is something like an upper bound also constructive of 5.4 times C plus D. Okay. Now to conclude, so we have some further, again with my student Harris, we have some further improvements recently on what is called the lopsided LLL, where you don't just coarse grain classify the bad events as independent or not, but as whether they're positively or negatively correlated. So here we are able to get some, so there's for example a classic result of Erdős and Spencer on Latin transversals. We are able to make it constructive. Moser Tardos in general does not apply to the lopsided local lemma, right? So we are able to get some of those. Some interesting open questions are, what is the LMR constant? Something like 2 perhaps. More interestingly, Shearer's stuff is based on an exponential characterization. Basically, he looks at all possible independent sets and so on, and shows that a certain a multilinear function has to be positive. Is there a better algorithmic understanding? I think that's a really interesting open question. We make some steps here, but I think that is really quite open. So by the way, Mario Segedi and the student Kashyap Kolipaka, they have some algorithmic understanding. So if you look at that body that so this body, they show that if your point lies to within, is fairly inside this body, if it is within 1 minus epsilon of the boundary, then you can actually make it constructive, right? So there is a notion of constructive for these problems where there are no underlying independent random variables, but how much exactly we can go is still open, right? But the other thing is, on the other hand, Shearer often is overkill, because Shearer's characterization is optimal, but that's only optimal for arbitrary events EI, basically, right? But in any particular application, you get concrete events which may not at all, can help you go beyond Shearer. So on the one hand, and Shearer is a limit. On the other, you can go beyond because it is best possible only for arbitrary events EI, basically. So these are some open questions. One other concrete open question is the independent transversals thing that I mentioned here. Okay, so I'll stop here.
So you mentioned Tardos
I see. So unfortunately not any simple looking thing. So we have to write some complicated conditions. In many cases the distribution is some, the distribution for partial resampling is natural. So for example, if an event depends on k variables, you choose some k prime smaller than k and make the distribution the uniform distribution on all the k prime size subsets, right. But unfortunately we don't have a crisp statement basically. Yeah.
Other applications of the stronger bound, namely that the probability of any event is not much larger than, under the final distribution, the satisfying distribution, not much larger than.
Are there other applications?
Other applications which use this, the fact that you have high mean entropy of the,
I see.
of the resulting distribution of the Moser Tardos procedure.
I see, and not to my knowledge. Yeah. So, I mean, we use it in our stuff, but in showing, for example, that for maxsat you can go beyond what the LL.
So
we use it. Yeah.
The fact that the distribution is property well for which event, which type of event.
Okay, so in fact, okay, so that's a very good point. In fact, let me tell you the following. So like Avi says, the fact that the min entropy finally is large can be used in the following way. So in fact, like I said, so suppose you have very large number of bad events, but you can assume a little bit stronger than the LLL condition, something like this. So recall that the LLL condition says that there should be these scalars xj that satisfy this property, right? Right. So suppose you can assume this, right? Then let's actually do the following. But suppose the number of bad events is exponential, right? How do we run Moser Tardos? In fact, let's do this, right? Let's only take the following core. So the core is the set of all I such that the probability of EI is not too small, is something like this, right? And just drop all the other events, right? And just run Moser Tardos on this core. You can show that this core is polynomial sized, right? And just run Moser, completely drop all the other events and just run Moser Tardos on these. And then for the rest, you just do a union bound based on the output distribution property, right? The output distribution property holds for moments and anything also. So you can also show concentration bounds. Yeah. So that's how we use our stuff. On the yeah. So the guys you dropped, you never even look at. Yeah. So one very interesting open question is there also. So therefore, you clearly get a Monte Carlo algorithm. So de-randomizing these, of course, is a very interesting open question. There's some partial progress, but there's a lot to be done in de-randomizing all these. So one thing is, can you at least make this Monte Carlo? And it's highly, it seems, how will you make this Monte Carlo? Because you don't even look at those bad events, right? And in some applications, you cannot check that. There's no obvious way of checking that that you have avoided all of those, right? But in some recent submitted work, we have actually shown that some of these can be made Las Vegas, basically because in fact not just at the end, but even throughout the execution, the Moser Tardos essentially it behaves like almost if you resample a variable, it's like you resampled it only because you sampled all the variables and the probability it turned out that this bad event was true, right? In other words, that Moser Tardos has a lot of random properties even while it's running, basically, right? So in fact, many of these problems of searching for checking if some bad event is true and so on is like finding a long path in a random graph, but it's like a random graph because the execution of MT largely is quite random. It's not like in a worst case evolution. So these paths will in expected sense will terminate very soon. So actually some of these can actually be turned into Las Vegas, not all. So something that we found we observed recently is in fact that so that's why I think that this MT process itself needs to be understood more. I think it is more than just an algorithmic version of the local lemma.